I think you'll all agree with me that her work is very interesting and that she's really good at communicating with to a broad audience as well. So with that, I'm happy to turn it over to Anjali.
Thank you, Mark, and thank you for inviting me to this awesome colloquium series. There was a great set of talks this morning, and so there's a lot of pressure to follow right after them. Like Mark mentioned, I recently joined the University of New Mexico as an assistant professor, and one of the major thrusts of the research in our group is atmospheric water harvesting, which is a new decentralized technology that can provide water resilience out here in the Southwest. So I want to kind of start with our big picture need of thinking about water disasters. Typically, we think about natural disasters and municipal drinking water disasters. And when we think about natural disasters, our minds automatically turn to photos like this. This here is a picture of Puerto Rico after Hurricane Maria in 2017. And the island had widespread infrastructure damage. They didn't have access to piped drinking water for up to 3 months, nor did they have access to a stable electrical grid for over a year. And when we think about municipal drinking water disasters, our mind turns to images like this. So this here is water in Flint, Michigan. From 2014 to 2016, school children in Flint were not able to drink tap water because of contamination from lead. So while these are localized, larger problems in different parts of our country, out here in the Southwest, we have specific niche, unique disaster or localized water use issues. The EPA estimates that up to 30% of individuals living on the Navajo Nation do not have access to piped drinking water, and instead have to drive up to 30 miles to a local well to fill up water in these large barrels that can be anywhere from 50 gallons to 250 gallons in size. But oftentimes, these wells can have these not safe to drink notices that are posted, either due to contamination from metals, like we heard earlier today, things like uranium, arsenic, and vanadium, but we can also have contamination from fecal matter. And so individuals may either have to drive to a further well site in order to pull water, or in extreme scenarios, we have this, where we end up transporting and delivering bottled water. Now, the reason that we transport and deliver bottled water during emergency scenarios is because it's safe, it's clean, and it's reliable. But the challenge with bottled water is that it costs anywhere from 300 to 700 times more than municipally treated water. So living here in Albuquerque, we would be paying a lot less. And that is a huge inequity issue. But what we see here is that there is an opportunity space for an alternative technology to maybe answer that need for safe, clean drinking water off the municipal drinking water grid that has that flexibility and safety of bottled water, being able to provide it anywhere at any time, but without the associated cost or waste. So how do we do that? Typically, when we think about getting water, we think of liquid water. We think of rivers, lakes, groundwater, oceans. But out in the arid Southwest, those may not be accessible. Rivers, for example, the Colorado River had to call a shortage this year. Our groundwater can be contaminated, like we said, with uranium, arsenic, or vanadium. But there is a reservoir that we haven't talked about yet, and that is the atmosphere. Now, the atmosphere is a freshwater reservoir that actually has 6 times more water than rivers, which is our primary drinking water source. And what I find most exciting about the atmosphere is that it is universally present. So whether I'm here in Albuquerque, or if you're in Utah or Montana, or if you're out in Flint or in Puerto Rico, the atmosphere is always around you, and you can harvest that water anywhere and at any time. So where did this idea of atmospheric water capture even come from? Well, this is what we call bio-inspired design, or biomimicry. This here is a photo of the Namib desert beetle. So as fog rolls in over the coast in the morning, those fog droplets will actually collect on the back of the desert beetle and roll down its back into the beetle's mouth. So the beetle effectively relies upon the atmosphere as its drinking water source, and it doesn't need a liquid water supply. So scientists and engineers love this concept, and they're like, we have to do this as well. And so over the last 30 years or so, there's been a lot of technology development in this water harvesting space. But really, there are still several unknowns that need to be addressed before this technology actually can get out to market and use. And namely, we'll be discussing 3 of those today. The first one is, what level of success will water harvesting technologies have in different climates? We understand intuitively that the amount of water vapor in the air varies depending on where we're at. Here in the Southwest, it's really, really dry and arid. But if I were to go to Houston or Florida, it would be extremely humid and I would probably be dripping sweat as soon as I landed at the airport. So clearly the amount of water in the air varies, and that probably is going to drive the level of success of different harvesting technologies. Related to that is understanding how much water we can pull off the electrical or not off the electrical grid. We're thinking of water harvesting as an off-grid technology to be used in localized use scenarios, rural areas, or after disaster relief, all of which areas we don't have access to a stable electrical grid. Therefore, we may have to rely upon renewable energy supplies like solar or wind. And finally, very important if we're thinking of this water supply as a drinking water supply, is understanding what is the quality of the water produced. Is it safe to drink? So the research that we work on spans across these technology readiness levels, starting at the basic technology to prove feasibility, to see does this even work? But beyond that, we have to span up these TRL levels into system development and operation at the pilot and full scale to really see whether we can deploy these technologies immediately or whether we're 10 or 20 years out from there. Before we get into how all these technologies work, I want to orient us into thinking about water in the atmosphere. So on the left-hand side here, I've got a phase diagram for water, and this may bring you back to your chemistry classes. On the x-axis, we have temperature, and on the y-axis, we have pressure. And this red line here kind of delineates the pressure and temperature regions at which water is present in a specific phase, be that vapor, liquid, or ice. And this blue hashed region here is water in our typical ambient atmosphere. We typically describe the amount of water in the air as vapor density, the mass of water over some volume of air. But the more colloquial way we refer to this is relative humidity. The simplest way to describe this is relative humidity is how close you are to the saturation boundary between your vapor and your liquid phase. So this upper blue dot here is water at a higher relative humidity. It's closer to saturation. And this lower blue dot here is water at a lower relative humidity or further from saturation. So the way that we typically think about how we will condense water is through cooling. Think of if you had a steaming pot of water and then you took a cool lid and put it right on top. That steam would automatically condense on the lid that you put on top of the pot because that lid is a cooler surface. So what we think intuitively is that the amount of cooling that we'd have to apply is going to be a lot more at a lower humidity, hence this longer line. And we use thermodynamics to calculate this. We actually find that as your humidity gets lower and lower, you actually require anywhere from 300 to 800 times more energy to condense that water from the atmosphere. And at lower humidities, this becomes even more challenging because you have this entire zone down here where your dew point temperature is below freezing. So you're just going to create frost. So the technological challenge that we're facing is how do we overcome the energy barrier at low relative humidities? Well, the secret to the sauce is a technology called a desiccant. So you may be familiar with desiccants as those little white packets that you may find in like a shoebox or in powdered food. And the reason that those little white packets are there is that they help collect water vapor from the atmosphere. So that water vapor doesn't impact the quality of your shoes, or it doesn't clump up your powdered food before you go to use it. And we can use that technology for this engineering purpose of water harvesting. So here on the left, we've got water vapor that's far from saturation. So these Mickey Mouse water vapor molecules are far away from one another. Let's just say a relative humidity of 30%. And what they'll do is they're attracted to the surface of a desiccant material and they'll concentrate on the surface. Then you can apply heat, solar thermal heat or electrical heat, to drive the water vapor off the desiccant surface into a smaller volume. So now you can see that these Mickey Mouse water vapor molecules are closer and more compact, and your relative humidity moves from 30 to almost 95%. And now you can simply do some sort of cooling, condensation through heat exchange in order to phase change this water to a liquid. Desiccants are typically configured in a very simple box, about a cubic meter in size, so the size of a U-Haul moving box. And you've got a layer of desiccants layered across the bottom, and air flows over this bed. And the way that it operates is at nighttime, you adsorb that water vapor, and then you expose it to sunshine during the day to desorb or release that water before you collect and condense it. The challenge is that most of our science and engineering research to date, particularly the state-of-the-art desiccant materials that are being discovered, are being optimized for humid climates. You can see in this graph here to the right that these warmer colors are showing that your water capture potential is anywhere from 3 to 6 times higher using these materials in a more humid area compared to out here in the Southwest. You can see these cooler tones happening here. So in order to optimize water harvesting for a Southwestern climate, we need to understand what are the climate dynamics that we have here. And the key to this is understanding the relative humidity and the amount of sunlight we have. The relative humidity out here in the summertime, particularly in the Southwest, is 10% to 40%. Very, very, very dry. But what we have in abundance is sunshine. And those of you out in Arizona, I know that you feel that summer love when it hits 120 degrees outside. We can use that to our advantage here. And the way that we're going to do that is by using what's called a photothermal nanomaterial. So here I've got a traditional desiccant material, and usually I'm going to apply heat to remove the water off the surface. But instead, what I'm going to do is I'm going to take this desiccant and coat it with a photothermal material. Photo meaning light, and thermal meaning heat. So when these materials interact with light, they're going to heat up. And this localized heating on the surface of your desiccant is going to drive the water off the surface. So we've looked into different types of materials that absorb light in the solar spectra. So in this graph here, the yellow line is the solar spectra. And you can see this black line here, this here is a carbon black nanomaterial, can absorb light completely in the solar spectra. And it actually heats up quite effectively. So this is just like putting a black car out in the sunshine for 5 hours. You sit inside and it's extremely hot. So the same way we are able to tailor make these desiccant materials by taking a base silica gel, exactly the type of material that would be in those little white packets in your shoebox, and coating them with materials to make them either black or red or green. And what this does is it allows you to cycle your material back and forth between adsorbing water and desorbing water over and over again throughout a day. Because we can take advantage of the abundant sunshine down here in the Southwest, when you expose a saturated desiccant to sunlight, it'll release water in the matter of 5 or 10 minutes, which allows you to cycle it back and forth over a day for up to 10 cycles to make up to 2.5 liters of water per meter squared surface area a day. Compare this to our traditional passive desiccant materials that only operate 1 cycle a day, adsorb at night, release during the day, and nothing happens. You have a 10 times higher capacity by understanding the location in which you're operating in and designing a material that is tailored to the conditions at which you want to optimize your water harvesting capacity. Not only are we tailor-making a material, we're also changing the configuration of the system, moving from a traditional way of doing these things to some sort of a cyclic operation to really take advantage of the resource that we have out here, which is sunshine. So this is stuff that we're doing at the bench scale, at the material scale. But now I want to kind of address those higher technology readiness levels by talking about the water quality that was produced. We did a year-long pilot study out in Arizona to look at the quality of water produced by different types of water harvesting devices. And this here is a representative graph of dissolved organic carbon. This kind of represents specific air quality emissions and parameters aldehydes, and carboxylic acids that may be given off through fuel emissions or industries that are ending up in your condensed water. The key takeaway from this graph is you see that your water quality varies temporally depending on when you're operating this technology. So the level of treatment that is going to be required will not only depend on location, but will also depend on the time of year that you operate. You will definitely require some level of filtration to remove this organic carbon, as well as some sort of disinfection to remove any sort of pathogens or bacteria that may be present in your water in order to make it safe to drink. So we've talked about materials, we've talked a bit about water quality, and finally I want to end with thinking about at a larger scale, what is the cost of operating all of this? And so now we're working on a techno-economic analysis to identify economic feasibility and sustainability of our technology. Starting out here with your power draw, whether you're using a free source like solar thermal heat, or whether you have to install new sorts of renewable energy like solar PV or wind to determine the cost of that. Then you've got your cost of the technology itself, depending on what sort of climate region you're operating in, and add to that the cost of the water that you're treating, in order to result in a final result of the cost depending on the volume of water that you produce per day in a certain area. So tying this all together to resilience, really what we find here is that technological solutions for water resilience are region and need specific. We can't take a solution that works out in the Midwest or the East Coast and transplant it out here in the Southwest and hope that it works. But what we do find is that atmospheric water harvesting can be viable off-grid for localized communities that are living off the grid or during disaster relief scenarios. So what's it going to take to make this happen? The first thing is that there are several companies that are already piloting these technologies. They're moving from a gallon to 10 gallons to even 1,000 gallons of water a day. But what these companies need to do is location-specific experimentation, design, and analysis. They need to stress test those technologies out here in the Southwest and see whether they're actually viable. Beyond that, we need to assess the costs, benefits, and uncertainties involved in scaling up and applying technologies at a practical scale. Sure, we've been able to develop novel materials in the lab, but do those actually scale up and function in the field? And finally, and most importantly, is understanding how users are going to interface with the technology. Will they accept it? Will they trust it? Will they use it? And will they maintain it? So I admit that I've been trained as a traditional engineer. I've thought about the mechanisms and the processes for how we design things and touched a little bit in economics. But as I move to my independent research career, I also want to bring in that social and human perspective into the work that we do. And I'm so inspired by the talks that happened earlier today, showing how we can incorporate local and Indigenous perspectives into science, engineering, and technology. So what I want to do is I want to learn from you, and I want to talk to you in order to not just educate myself and influence the research that I do, but also think about how I educate the future generation of students in the classroom and who come through the lab to enable them with that holistic perspective of environmental justice, so that as they go forth into their own engineering careers, they too think about how users interface with technologies, not just the mechanisms and the cost. So with that, I want to thank you all for listening today. I want to thank the Resilience Colloquium and Mark for inviting me, as well as an awesome team of collaborators and researchers. And I open the floor for questions now. You can also follow up with me via email at anjaliem@unm.edu. Thank you so much.
Wonderful. Thanks so much, Anjali. It's a fantastic presentation, as expected. Really good, really good at communicating what you do, even though it's so technically complicated, but it makes sense even to someone like myself who fears chemistry. So I do see some, or at least I thought, oh, I remember now. There was a question in the chat. Patricia Townsend had asked about the necessity for water treatment. Why does this require any treatment? It seems like it'd be almost like DI water.
Yeah, so the original thought when people did water harvesting was that it would be completely pure water if you're taking water out of the atmosphere. But air pollution, we find, does impact your water quality. Depending on the location that you're operating in, you can have specific organic molecules in the air, and you can also have metals that are associated with dust that condense into your water that you then need to remove. The metals that we've found are things like iron and aluminum and copper that are a little bit higher than your EPA regulated limits, and so you need to apply treatment. Your organic carbon as well, you need to be able to remove that if you're going to apply any sort of disinfection. Organics plus disinfection measures can actually form carcinogens, so we need to remove that.
Could see that being tied back to our discussions about wildfire this morning as well, right? Those conditions are going to shift over time. There were a couple other questions in the thing, and it's still rolling, so it's hard for me to follow. But Barb's Marone had asked one that was kind of on my mind as well. And I'm picturing like actually having like a backpack that looks like that bug, so I can just like go jogging and like just like do my water harvesting while I'm out on the go. But she's asking, to what extent are you using biomimicry to actually look at the material design aspects?
Yeah, so what we found with biomimicry is that those desert beetles are tailored to pull in fog. And fog is different from water vapor at low aridities. So while original materials were being designed in a bio-inspired way to pull in already concentrated aerosol droplets, that doesn't necessarily work in low humidity climates. So for low humidity climates, you now have to think about maybe how a cactus pulls in water through its needles. And it's essentially a pressure differential between the tip of the needle and where the base of the cactus is. And so you use that same thought about a pressure differential as how water collects onto a desiccant surface.
Wonderful. And Courtney Flynn at Utah State posed a question that I'm sure is on a lot of people's minds, some variation of this. But you know what it really comes at is, how big of a reservoir are we talking about, and when will Texas sue us? Right.
Yeah. It's funny that depending on who you're having a dialogue with, whether this question comes up or not. And it turns out that when you have a more broad community that you're speaking to, this question comes up a lot. And I think it hasn't been addressed yet, but it needs to be addressed. And so that's kind of where I would bring in water rights individuals or environmental lawyers, individuals, or people who work in environmental justice, to think about what these water rights are and whether that's something that we have to consider for the atmosphere. Yeah. It is a discussion that needs to happen.
I think Jake and I are going to go into business atmospheric water speculating and buy up everybody's atmospheric water rights so that then you can buy it back from us. But speaking of which, looks like Jake has a question.
Yeah, no, great point, Mark. So I'm Jake Collis. I'm a research professor at UNM, and my specialty is evaporation of water from reservoirs. So I have a question for you. So your photothermal nanomaterial you're adding to the desiccants, does it impede the absorption of the desiccant?
Oh, you hit on a perfect question. Yes, it does. And so the research that we're working on right now is how to tailor a material that can both adsorb and desorb effectively. So essentially what you have is, think of like, oh, it's like a wiffle ball or like a golf ball that has holes, and that's a desiccant. But then when you stick nanomaterials on top, you may actually be blocking those holes of a wiffle ball, impeding your absorption. And so now what we're trying to think about is different ways of designing these materials so you still have those holes accessible for water collection, while also making sure that it's a dark enough color to heat up to release that water.
Yes,
those are the challenges that we're addressing.
Yeah, perfect. Yeah, I mean, because here in the Southwest, we're looking at relative humidities of 5%. And most of your examples, you're talking 30, 40%. What's the lower bounds of a desiccant for absorbing?
Yeah, so it depends on the type of material. The materials that are ideal for collecting water at even lower humidities, 5, 10, 15%, those are zeolites, and they're great at collecting water, but they're also great at keeping the water stuck.
Yeah.
Which means you have to apply even more heat to release that water. And so ultimately what you have here is a trade-off between a great adsorber and a great desorber, and trying to make the best type of material.
Fantastic. Well, your research is amazing. I love what you're doing. And like what Mark was touching on, like in the future, we'll put a bunch of these atmospheric absorbing materials downwind of the reservoirs so we can recapture the water that we're losing through evaporation. So
Yes.
so Texas is to get all our water.
They'll still sue us. It's okay.
Yeah, they will. Great talking.
All right. Well, let's everyone thank Anjali for a really, really nice talk and great questions and dialogue thereafter. We need to unfortunately keep moving, but thanks so much, Anjali. It was really fascinating presentation.